Okay guys, today we are starting our lesson on zeros and factors of polynomials. Alright, so actually before we get into it in our notes, I would like for us to do a problem from the lab manual first thing. This is number 2 from the section, actually, remainder theorem section. That was our previous lesson, but we are going to actually use it here in factoring polynomials pretty heavily. So let's start out with this question number 2. Remember, remainder theorem tells us that if we divide a polynomial, p of x, by some linear factor x minus c, right? So here c is 1, so we're looking at x minus 1. If we divide p of x by x minus 1, the remainder is going to be equal to p of c. We're being asked here to use division and remainder theorem to evaluate p of c. And then if c is a 0, we want to factor the polynomial completely. All right, so let's use synthetic division with 1. So we put 1 in the upper left-hand corner. We follow with all the coefficients here. We have 1, -3, 3, and -1. We bring down our leading coefficient. We multiply, we get 1. We add together, we get -2. We multiply, we get -2. We add together, we get 1. We multiply, we get 1. We add together, we get 0. So our last term is our remainder. Since our remainder is 0, this tells us that p of 1, right, p of c, is equal to 0 by our remainder theorem, right? Remainder theorem tells us this. Remainder theorem. So if remainder theorem tells us this, what does factor theorem tell us? Well, factor theorem tells us in this case that x minus 1 is a factor of p of x. Awesome. So furthermore, this means that p of x can be written as the factor that we just found, so x minus 1 times the quotient, what was left over. Remember, we find the quotient by looking at the coefficients that are given to us underneath the line here. We have 3 terms, so we're going to have constant x term, x squared term. So we have x squared minus 2x plus 1, right? We use our coefficients to give us our quotient. The instructions do say to factor the polynomial completely if c is a 0. In order to factor this completely, we need to just factor out this last quadratic here, which is not too hard, right? We just need to come up with something that adds together to give us -2 and multiplies to give us +1. That's -1 and -1, right? So these are all of the factors of p of x. We can also, if we wanted to, rewrite this as x minus 1 cubed. These are the same, right? Either of these would be correct. We've factored the polynomial completely, right? These are all of the factors. Very cool. So, okay, so there are a few ways that we'll be asked to factor a polynomial. Write the polynomial as a product of linear and irreducible quadratic factors . with real coefficients. Or, sometimes both, and as a product of linear factors with complex coefficients. So, first of all, we know what an irreducible quadratic factor looks like. It's just an irreducible quadratic, right? Which is ax squared plus bx plus c for a quadratic that has non-real roots. A linear factor, which both of these talk about, a lot of times we see linear factors and they look like this, right? X minus c. But a linear factor can also actually look like ax minus c. So technically a linear factor can have a coefficient on the x. When we are asked to write something in root form, we definitely want to make sure that our x has a coefficient of 1. But if it's just asking for a product of linear factors, or it's, linear factors, you can have a coefficient on the x. That's totally fine. The reason it's called a linear factor is because these look like lines, right? The equation of a line is ax plus b. They're polynomials of degree 1, right? Linear factor. So we've seen linear factors, of course, that are like x minus 5 or x plus 1, where we have a real root from that linear factor. We've also seen linear factors that have complex roots, right? We've seen x minus, 4 plus I, or x minus 2 minus 3i, all kinds of stuff. What is this saying? Well, our first one here, product of linear and irreducible quadratic factors with real coefficients. We can always write a polynomial as, right, its leading coefficient, and then x minus root, x minus root, x minus root, etc. Right? But sometimes these roots are real, and sometimes these roots are non-real complex numbers, right? So in order for us to write a polynomial where all of the coefficients are real, some of them can be linear. The ones that have real roots can be linear. But if we have non-real roots, right, we want to write it with real coefficients, we have to multiply some of the roots together in order for us to have real coefficients, right? We'll see an example of this in just a second. Let's say we were given f of x equals x cubed plus 5x squared plus 11x plus 10. And let's say, like our previous remainder theorem problems, we're asked at first, is x equals -2 or x equals -3 a root? When we have something like this, a lot of times we'll be given, a factor or a root or something, maybe a graph, that will tell us one of the roots so that we're able to factor that out and then solve the rest easily, because we can't factor something like this as far as we know. We'll have another video on factoring higher order polynomials. There are some higher order polynomials. By higher order, I mean degrees that are larger than 2, right? We can easily factor a quadratic using our quadratic formula, but when we have a degree of polynomial 3 or larger, we need to use tricks or have a factor, have one root that we know. So let's use synthetic division to figure out which one of these is a root. Let's start with -2. So our coefficients are 1, 5, 11, and 10. We bring down the 1. We multiply, we get -2. 5 plus -2 is 3. -2 times 3 is -6. 11 plus -6 is +5. 5 times -2 is -10, and 10 plus -10 is 0. So, of course, we get a remainder of 0 here, so -2 is the root. Let's do the synthetic division with -3 just for the extra practice. Okay, so again, our coefficients 1, 5, 11, and 10. We bring down the 1. We have 1 times -3, which is -3. We have 5 plus -3, which gives me +2. We have -3 plus 2, which gives me -6. We have 11 minus 6, which gives us 5. And then we have -3 times 5, which is -15. We add these together and we end up with a remainder of -5. So this, of course, means that this is not a root. So -2 is a root. This one means -3 is not a root. All right, well, if -2 is a root, of course, we're talking about zeros and factors of polynomials. We're talking about factoring polynomials. Let's factor this polynomial. So x equals -2 is a root. That means that we can write f of x as the factor x plus 2 and its quotient. So what is the quotient here? Again, we have 3 coefficients. This is going to be our constant term, our x term, and our x squared term. So we have 1 times x squared, or just x squared, plus 3 times x, which is 3x, plus our constant term of 5. We have a factor here that is linear, and we have a factor here that is a quadratic. We can't tell just by looking at it whether it's irreducible or not. So let's go ahead and plug it into the quadratic formula to see what our factors are. So x equals -3 plus or minus the square root of 3 squared minus 4 times 1 times 5 over 2 times 1. We have -3 plus or minus square root of 9 minus 20 over 2. So -3 plus or minus the square root of -11 over 2. So what does this mean? Well, we have a negative under the square root, which means we have a negative discriminant, which means we're going to have I, right? When we simplify this, we're going to end up with I. So this is non-real complex roots. Which means that this is an irreducible quadratic. So this guy right here is actually the first type of factoring, right? This is a product of, this is the polynomial as a product of a linear factor and an irreducible quadratic. So this is one of the ways we would want to factor, or could be asked to factor. So this is linear and irreducible quadratic with real coefficients. I'm squeezing everything in. I'm so sorry, you guys. With real coefficients, right? All of these coefficients are real. Okay, let's keep on going and see what the rest of our roots are. So we end up with -3 plus or minus. We want to pull out that I. We have the square root of 11 over 2 So our two roots that we have are -3 minus I times the square root of 11 over 2. These clearly are non-real complex roots. So if we wanted to write f of x completely factored, right? So as a product of just linear factors, regardless of whether the coefficients are real or non-real complex roots. We have our first root of x plus 2. Then we have one root of x minus -3 minus I times the square root of 11 over 2. And -3 plus I times the square root of 11 over 2. This is a product of linear factors with complex coefficients. Okay, let's check out one of these in the lab manual. This is actually under the section called Zeros and Factors of Polynomials. This is number 6. So we're given this function, and it says, using division, show that x squared minus 1 is a factor of g. X squared minus 1 is not one of the factors that we can use with synthetic division. Remember, synthetic division, it has to look like x minus c. So we have to use long division here. So let's set up that problem. We have x squared plus 0x, right? Very important that we don't forget our placeholders. And then underneath we have x to the 4th plus 2x cubed plus 5x squared minus 2x minus 6. Okay, let's start dividing. So we have x to the 4th divided by x squared. That leaves us with x squared. We want to put that above the 5x squared. We multiply through here with the x squared. We get x to the 4th plus 0x to the 3rd minus x squared. We subtract all of that. We have 2x cubed, and then minus a negative gives us plus 6x squared. Minus 2x, we bring that down. And then we start over again. So we divide first term by first term. So we're dividing 2x cubed by x squared. We're left with 2x. So we have plus 2x up here. 2x times x squared is 2x cubed. 2x times 0x is 0x squared. And 2x times -1 is minus 2x. We subtract. We're left with 0. And then 6x squared minus 0x is 6x squared. And then -2x minus a -2x, which is plus 2x, those guys actually also cancel, so we end up with 0x here also. Let's bring down this 6. We divide first term by first term, so 6x squared divided by x squared gives us 6. That's our constant term. We have 6 times x squared, we get 6x squared plus 0x. 6 times -1 is -6. We subtract all of these. We end up with these cancel. 0x minus 0x is just 0x. And then -6 plus 6 is 0. So all of this leaves us with 0. Is it a surprise that we got 0 here? It's not, right? We know that if something is a factor of a function, then it should give us a remainder of 0. So this is not a surprise. The quotient is this guy, right? This is the quotient. So this is a factor. All right, it asks us to determine all real and non-real complex zeros of G. So first of all, before we even start, if we know that x squared minus 1 is a factor, right, then we know that we can write G of x as x squared minus 1 times x squared plus 2x plus 6. We don't know what the factors of this are necessarily yet, but we do know what the factors of this are, right? We have x squared minus 1. That's a difference of squares, which means we can write this as x plus 1 and x minus 1. Which means that we have a root of -1 and +1. How many roots are we going to have total of this function? Well, remember our number of roots is equal to the degree. The degree is the highest exponent, so we have 4 roots here. So we've found 2. We need to find 2 more. Looks like those last 2 are going to come from this quadratic. Let's factor it. So we have -2 plus or minus the square root of 2 squared minus 4 times 1 times 1 times 6, all over 2 times 1. So we have -2 plus or minus the square root of 4 minus 24 over 2. We keep going. We've got -2 plus or minus the square root of -20 divided by 2. -2 plus or minus, we need to pull that I out very first thing. Can we simplify 20? We totally can. What's a perfect square factor of 20? 4 right off the bat. So we've got -2 plus or minus, when the 4 comes out, right, it becomes 2 because we have to take the square root. So we have 2i times the square root of 5 divided by 2. Since I have 2 in the bottom, I can divide both terms by 2. The first term, -2 divided by 2, is just -1. And then my second term, 2i square root of 5 divided by 2, is just going to be I square root of 5. So we have 2 roots. One is -1 plus I square root of 5, and one is -1 minus I square root of 5. Those are all of our roots. Last question is asking us to write G as a product of linear factors with complex coefficients. So we write it as all linear factors. We do have some complex roots, right? Some non-real roots, but that's okay because we can have all complex. Let's write it down here so we don't run out of space. So we have x minus, x plus 1, and x minus 1. We already knew those. And then our last ones are x minus -1 plus I square root of 5, and x minus -1 minus I square root of 5. And that is the answer. Okay. So we've seen 3 of those. Let's go back to our notes. So before we move on, one thing I would like for us to talk about super quickly, refresh on. Remember, if a polynomial has a non-real complex root, its conjugate is also a root. Right? This is the whole thing with irreducible quadratics, right? Whenever a quadratic had one non-real root, then it also had the complex conjugate as a root, right? Because of the quadratic formula and that plus and minus in there. So that is going to play into these next type of questions. Sometimes you'll be asked to write a polynomial that has a few given specifications. For instance, example, 3 plus I and 1 minus 2I are roots of a fourth degree polynomial with leading coefficient 1/5. Find all roots and write this polynomial, we'll call it P of x, as a product of linear factors. Okay, so the first thing we're asked to do is write out all of the roots. So how many roots do we have here? Again, the number of roots is equal to the degree. What's our degree? It's 4, right? So we have 4 roots. 1, 2, 3, 4. First of all, we know we have 3 plus I. But we also know our fact, right? So if we have a complex root, a non-real complex root, its conjugate is also a root. So what is the conjugate of 3 plus I? It's 3 minus I, right? We flip the sign on the imaginary part. Similarly, if we know we have the root 1 minus 2I, what's our last root? 1 plus 2I. How can we write P of x? Well, we can write it as a product of linear factors if we write our leading coefficient, and then all we have to do is write x minus each of these roots to give us the linear factors. So we have x minus 3 plus I, x minus 3 minus I, x minus 1 minus 2I, and x minus 1 plus 2I. Notice I put parentheses around the coefficients, around these non-real roots, right, for each of these factors, right? And that's because of that negative. It's kind of important. Okay, what if the problem also asked us to write P of x as a product of linear and irreducible quadratic factors with real coefficients? Okay, so are any of these linear factors going to have real coefficients? No, right? These all have non-real roots, right? So because of that, we're going to have to turn each of these linear factors into the corresponding irreducible quadratic. Let's do that really quickly. Let's do that for each of these. So I'm going to start with, over here, x minus 3 plus I times x minus 3 minus I. We had a very specific method for doing this, right? We distributed the negatives, Then we grouped the non-imaginary parts together, so the real part, so x minus 3 minus I and x minus 3 plus I. And then we saw that these were conjugates, right? We had negative and positive, same thing in front, same thing behind. And then we used the difference of squares, right? So if we have a minus b times a plus b, it's equal to, all of these are equal, it's equal to a squared minus b squared, right? Then we changed I squared to be negative 1, and then we FOILed out this first part. So we have x squared minus 6x plus 9 plus 1, right? Minus a negative 1 is plus 1. So we end up with x squared minus 6x plus 10. Why don't you guys do the same thing with this second pair of complex conjugate factors? Pause the video and check your answer when you're done. All the steps are here. The only thing that was really different from last time was that we had a coefficient on I, so we had to sort of make sure that we distribute that squared to both the 2 and the I, and it ended up being plus 4, and we ended up with plus 5 in the end. So now we have p of x is equal to 1/5. Instead of writing, x minus 3 plus I times x minus 3 minus I, we have shown that that is equal to x squared minus 6x plus 10. And then next, instead of writing x minus 1 minus 2i and x minus 1 plus 2i, we have shown that that's equal to x squared minus 2x plus 5. Now, all of the factors have real coefficients, even though they're quadratic, and this is the answer, right? Both of these are irreducible quadratics. Let's try another. So, example, give a polynomial that p of x such that we have the following. We have a degree of 5. We have zeros at 2, -4, and -3, I. X equals 2 has a multiplicity of 2. And the leading coefficient is 4. Okay, let's say, I don't want to have to write all of this out, but let's say that we are asked to factor it in the 2 ways from the beginning. So factor it in the 2 ways listed at the beginning of this lesson. All right, so first good way to start this is to figure out what your roots are. How many roots are there going to be? Again, number of roots, same as the degree. So since our degree is 5, that means we have 1, 2, 3, 4, 5 roots. All right, our first root is 2. What does the question say about the root of 2? It says it has a multiplicity of 2, right? what does a multiplicity of 2 mean? We're going to have 2 of them in our list of roots, right? So we have 2, a second 2, then we have -4, doesn't say anything special about that, and then -3i. So we're still missing 1, but what do we know? We know that because we have -3i and it's a non-real root, then its complex conjugate is also going to be a root. So if we have -3i, complex conjugate, we want to flip the sign on the imaginary part, so that's +3i. Awesome. Those are all of our roots. So one of the ways that we want to write this, right, one of the ways listed at the beginning of the lesson was to write it as a product of linear factors, right, with complex coefficients. We have all complex roots here. We have 5 roots, so p of x equals, first things first, we cannot forget the leading coefficient of 4. Then we have x minus 2, right, with a multiplicity of 2, so exponent 2. Then our next factor of x plus 4 for this guy. Then x plus 3i, right, x minus -3i is x plus 3i. And then x minus 3i. This is a product of linear factors, so we are totally done with the first one, right? So this is product of linear factors with complex coefficients. Okay, so in order to write this with real coefficients, we've got to get rid of these guys, right? Which means we need to find what these 2 linear factors are in irreducible quadratic factor form. So let's take these out to the side. We have x plus 3i and x minus 3i. These on their own are complex conjugates, right? We have one thing plus an imaginary part, and then one thing minus that same imaginary part. So we actually don't have to do the whole distributing and regrouping thing. We can go ahead and use difference of squares here. We have a plus b times a minus b, so we have a squared minus b squared. X squared minus, we distribute this squared, so we have 9i squared. I squared becomes -1, so we end up with x squared plus 9. So everything here is the same until we get to the factors with non-real coefficients. We have our leading coefficient, x minus 2 squared, x plus 4, and then instead of writing our linear factors with non-real coefficients, we'll write it as the irreducible quadratic factor that we just found, x squared plus 9. And then all of this together will be a product of linear and irreducible quadratic factors with all real coefficients. And that's it. Not sure what happened to my microphone or the video for the rest of this, but I guess I'll do the sign off from here. Thank you guys for watching, and I'll see you next time.